I'll jump right in then, if I may. Hello, everyone. Good morning or good afternoon, wherever you may be. My name is Anthony Price. I'm the current chair of the SEG Regional Advisory Committee for Europe, the European Advisory Committee, of course, for the European parts of the membership. So I'd like to welcome you all today to our regular webinar, and I'll hand over to Laurie to introduce our speaker today. Thank you for your attendance.
Thank you, Anthony. Today we have a great pleasure to have Johannes Stoll present for us on drone EM, some directions for the future. Johannes has a background in geophysics and electrochemistry and was active in several positions in the oil and gas industry and research institutions. Johannes is the founder and CEO of Mobile Geophysical Technologies and has 20 plus years of experience as an active exploration geophysicist. Today, he's going to talk about EM. And so airborne electromagnetics has evolved rapidly, driven by the growing demand for natural resources and the shift to CO2 net zero emissions economy. The need for more advanced exploration tools is stronger than ever. And as airborne electromagnetic systems rely on technologies from outside geophysics, the fast pace of innovation and product obsolescence presents new challenges. In the last decade, breakthroughs in geophysical sensors and platforms have led to the rise of drone-based AEM, unlocking new possibilities for subsurface mapping. This presentation will explore the latest in AEM sensor systems, their drone integration, and the exciting future ahead for exploration. So without further ado, welcome Johannes Stoll.
Good morning, everybody. I'm very grateful to present my presentation I have given already last year in October on the last drone summit. It must be, for some of you, it must be very early. Some of you may be already very late. So welcome everybody. I would like to introduce you to some exciting news, I hope exciting news, in drone electromagnetics. The title is Some Directions for the Future. And here in the first slide, you see the drones which were developed and used by MGT in the last 10 years. MGT is not a manufacturer of drones, but over the last 15 years, MGT always had a strong collaboration with UAV manufacturers in Germany, mainly in Germany, but also outside Germany. So just to give you an overview what MGT represents, MGT was founded in 2011 in Germany. And since that time, we had the opportunity to be active in several areas throughout the world. Currently, MGT is negotiating with partners to found MGT Global in Golden, Colorado, and also to found a second company, 4D Logics, which the purpose of the two companies is to broaden our portfolio and also to establish a global network that allows to offer our products worldwide. So we currently we represent, we were active in more than 15 countries. I think we can say we are already 15 years plus in the sky, and we conducted around 1,000 missions. So yeah, this is our global network. We try to plan in Southeast Asia, in South Africa, and in North America. Today I would like to introduce you into drone-borne electromagnetics, and will focus on mainly three topics. First, what are the most successful platforms since now, and what's going to become maybe interesting for the future. Second, I would like to speak a little bit about the critical height effect of frequency domain EM systems. This is currently one of the most exciting questions I heard about in the drone EM community. And lastly, I would like to speak about the resolution of semi-airborne electromagnetic methods, which rely on numerical case studies, but also on field experiments. And finally, I summarize what I think could be the directions for the future. Yeah. Drone magnetics became already a standard, so I don't think I don't want to speak about this any longer here. In the historic developments of airborne EM systems, mainly are TX, RX configurations. These are loop systems, which are either attached rigidly below an aircraft or towed behind the aircraft. But there is a demand for time and costs. So drones, I think, have the great potential to make a difference to traditional AEM systems in special environments. So what is the for those who are not very familiar with airborne electromagnetics? Airborne electromagnetics are divided into two hemispheres. One is time domain electromagnetics. This comes from the fact that the source is quiet for a certain period of time, and then switch to the opposite sign, whereas frequency domain electromagnetics uses a signal which is always on, but alternating. So it switches from positive to negative. This is the only difference. But this difference is important because for the time domain EM, when the transmitter is off, the receiver sees only the secondary field, which has big advantages, but also disadvantages. In the frequency domain EM, the primary source is always on, so all data processing interpretation has to deal with the primary source. So both are of moving type. This is the standard in airborne electromagnetics. Always the source and the receiver are attached to the drone or to the air platform. Some explanations about mutual coupling and the effect of frequency on the response. Assume there is a loop and a current is fed into the loop. Electric dipole is created, which induces eddy currents in the subsurface, which produces a secondary magnetic field that can be measured by a receiver, which is either on the surface or airborne. But with as a function of frequency, response depends on the frequency, the amount of electric current, or the amount of the portion that is induced in the subsurface depends on the frequency. So for a loop system, a vertical magnetic dipole system, the in-phase and out-of-phase part depend very much on the frequency. This is important because the amount of induced field depends on the frequency and is dominated by the by the separation of the Tx and the Rx. This is in principle similar for the horizontal electric dipole. If there is a horizontal electric dipole on the ground and you perform EM measurements, the response also depends very much on the frequency and on the conductivity of the subsurface and the separation of the transmitter to the receiver. For low frequencies, the response approaches a fixed value, whereas it becomes very weak for higher frequencies. So all AEM methods require on a magnetic dipole moment. But in order to look very deep, the dipole moment has to be very, very big. For example, the megatem system. In order to look almost 1,000 meter deep, you need an electric magnetic dipole moment in the order of megaamps square meter. So those systems usually feed several hundreds up to 1,000 amps into the loop to generate a magnetic dipole moment of this kind of order. In order to achieve this requires a very heavy system, a very heavy loop, and a generator that allows to feed in to generate those electric currents, to feed in electric currents of this strength into the loop. So it's clear that very heavy helicopters have to be used to carry those airborne EM systems. There are smaller ones which were developed already decades ago, but they can look only a few hundred meters deep. So physically, there is a limit, a physical limit that do not allow to go beyond to look deeper for airborne EM systems. Here you see the SkyTem system, which is one of the biggest one. Here you see the loop, a big loop with a diameter of 20 meters, and the receiver, the magnetometer, the transmitter loop. The distance is more than 40 meters to be not affected by the noise generated by the helicopter. There are other systems, frequency domain systems. Here you see the DCAM system, usually used as a standard by the German Geological Survey. It was developed by Fugro Airborne Surveys in Canada. Here you see another system, spectrum system. It has a loop which goes around the aircraft from the two wingtips to the rear and the front part of the aircraft. But this it generates also a very strong magnetic dipole moment. This is an alternative where the magnetometer is towed behind the aircraft. Yeah, the receiver is usually towed more than 100 meters behind the aircraft with a second magnetometer to measure the total magnetic intensity. There are now other frequency domain systems of moving type where the receiver and the source is attached to a drone. Here you see a prototype developed by Radai in Finland, Oulu. It uses a fixed transmitter loop and an airborne receiver. The depth, this is what they specify, is down to 300 meters. They use only 3 frequencies and the 3-component EM receiver. So flight speed is around 20 meters per second because it's attached to a VTOL, vertical takeoff and landing drone. The flight endurance is around 75 minutes, and the sample rate is 1 hertz. SkyTem, in collaboration with a drone manufacturer in Sweden, tried to develop a SkyTem system carried by a very, very heavy lifter from Thunderbolt. Here you see the EM system attached to this heavy lifter drone. It's the manufacturer is Thunderwasp TS drones in Sweden. Here you see a photo of this monster drone. This was a joint project by SkyTem, Thunderwasp, and other research institutions in Norway and Sweden. The maximum takeoff weight is 700 kilogram. The empty weight is 300 gram, and the maximum payload capacity is almost 400 kilogram. With 300 kilogram payload, it can fly around 1 hour. Another EM system, which I think is a very, very smart development of the last 2 or 3 years, is a drone and a EM system from Geonics, using the EM61 Lite from Geonics. Tobias Leininger from Aerotech in Florida integrated it on a drone. I think this is a very, very sensitive time domain EN system that allows to detect and locate very, very small metal objects in the ground. The lightest object they have ever discovered had just a small metal wire of a weight of a few tens of grams, 50 grams or so. In the last 5 years, a lot of efforts were undertaken to look deeper, and it's clear that due to the vast amount of power that is needed to look very deep into the subsurface. The idea was developed to use a grounded electric dipole and fly and attach the receiver only to a platform, to an aircraft platform. Here you see the principle of the drone, of the semi-airborne electromagnetic method. It uses an horizontal electric dipole, two grounded electrodes, which are connected by a long electric wire. The spacing between the electrodes is in the order of a few 100 meters up to several thousands of meters. But the physics becomes a little bit complicated because it's clear that if you use here a drone, you always fly from the near field through the transition zone to the far field, which are characterized by completely different dependencies of the field of the depth of investigation depends not only on the frequency, as it is the case in the far field, but in the near field, it depends also on the geometry. So it became very clear from the beginning this will have an impact on the interpretation of the response functions of those systems. In 2016, a joint project was founded in Germany to set up an semi-airborne exploration system that allows to explore mineral deposits. And at that time, a very heavy EM system was used that could be only carried by a heavy helicopter. So the BGR, the helicopter from the German Geological Survey, was used to carry this system. The DESMAX project, DESMAX is the abbreviation for Deep Electromagnetic Sounding for Mineral Exploration, tried to develop this method. And so it consists of the development of the method, the sensor development, to conduct reconnaissance flights, develop 3D inversion codes, and also try to improve the geological and mineralogical interpretation. So first steps were already undertaken to develop the semi-airborne electromagnetic method 10 years ago. So, but with the time, it became an interesting question whether such a heavy semi-airborne EM system can also be carried by a drone. So MGT developed in 2018 a system that weighs less than 10 kilograms. And due to this lightweight, it was able to attach it to an octocopter. On the left side, you see an octocopter that was customized and specifically developed for these purposes. The system in 2018 consisted of an EM data acquisition system that was attached directly to the frame of the drone, an inertial navigation unit, a flux gate magnetometer, which is very light. The flux gate magnetometer we are using weighs around 600 grams, and the 3-component EM sensor. In 2023, MGT undertook semi-airborne EM measurements in Canada in collaboration with Rosor Corporation in Toronto. ROSOR uses a hybrid gas-electric copter that can fly with that load up to 1.5 hours. So it became clear this could be a perfect solution to perform especially EM service in areas which are almost not accessible. Due to this very long endurance, huge areas can be achieved in one day. So we proved that 150 kilometers are feasible in one day, which is an extraordinary production rate at that time. The grounding of the electrodes can be a very tedious thing, especially on the Canadian Shield. But there are a lot of mud holes which allow to ground the electrodes very effectively, even if the environment is hostile and the temperatures are very low. In order to generate enough signal, a transmitter is used that outputs up to 25 amps into the wire, into the grounded wire, which generates an excellent signal that can be followed and picked up to several kilometers away from the cable. A third alternative was developed in 2023 by MGT for a client in Indonesia. It's a fixed-wing aircraft which weighs 25 kilograms. Of course, it needs a runway at least 150 meters long for takeoff and landing. For the first time, we developed an aerodynamic bird which contains the three-component EM sensor in the front part and the navigation unit in the rear part. During takeoff and landing, the EM bird is attached to the drone but released once the aircraft is airborne. This work was done in collaboration with Hanseatic Aviation Solutions in Germany. Here you see a result from a small of semi-airborne EM measurements taken on a small island in the Moluccan Sea in Indonesia. The red colored area indicates a very high conductivities, electrical conductivities, which is obviously a good indicator for seawater intrusion into the island. In the center part, we see some sedimentary layers, and in the eastern part, we see the conductivity is moderate, but we see some good indications for low conductivity zones in the subsurface, which could be associated with some mineralized zones. Now to another topic, the critical height effect of frequency domain EM systems. Assume you are conducting frequency domain EM measurements using the EM31 instrument from Johannes, which is widely used for near-surface electromagnetics, for near-surface electromagnetic surveys. So assume for a while, if it's on the ground, the response is almost zero. Or the depth of investigation is very, very small. If you lift it from the surface, the response immediately will change. This relation is shown here in this graph. On the horizontal axis, you see the depth normalized to the separation between the TX loop and the RX loop, the source and the receiver. The spacing, the separation between TX and RX here is in the order is almost 4 meters. So one would indicate a depth of 4 meters, but the relative response versus depth show it peaks at a much smaller depth, around 0.3. So it's less than 2 meter depth, the depth of investigation. So most part of the response, most information for this system is gained by a depth around between 1.5 to 2 meters. Yeah. All other response from deeper zones make less contribution to the response you measure at the surface. And I think this is important for our discussion to integrate those frequency domain EM systems to drones, because we are required to think thoroughly about the response, how the response changes if we attach such a system to a drone and lift it up to several meters. I would like to demonstrate this in the next plot. In the left graph, on the graph on the left side, the EM, here you see the response as a function of the induction parameter. This is a typical response which is seen for all airborne EM frequency domain EM systems. But if you calculate the response for such a system on ground, it looks completely different. The biggest difference is in the blue curve here, and in blue means the real part and red the imaginary part. The blue part for the ground, the system on ground, is negative, but for the AEM system, it's positive. The only difference is this is airborne and the other one is on the ground. So there must be a critical height where the response moves from positive through 0 to negative. And this is this I call critical height. Yeah. I did some calculations, very simple calculations to demonstrate this. Important is to understand what happens at the moment when the drone lifts this frequency domain EM system and gets to the critical height. This is shown here. So again, important is to understand when the negative response here gets approaches 0, and with increasing separation from the increasing height, flight altitude, becomes positive. So here you see what happens. Here I plot the amplitude and the phase, or real part and imaginary part. And for the ground type curves, for the frequency domain EM system on ground, if you slowly lift it away from the ground, the response is still negative, but at a certain height, at the critical height, the system a few the response changes very, very rapidly within centimeters, goes through 0 and becomes positive. So if you would use a frequency domain EM system on a drone and fly always at the critical height, you wouldn't be able to evaluate your data or to estimate the response, because it depends very, very much on the critical on the flight altitude, and you would be required to correct for it. So a ground-based sensor, the coil separation substantially exceeds the sensor height. Sensor height is negligible compared to the coil separation. For AEM systems, in-phase component reaches high positive values as EM response approaches the inductive limit, whereas the ground sensor, the in-phase component reaches a large negative value. So important is there is a sensor height where the in-phase becomes 0 at the inductive limit. This is the indicator that the sensor is at a critical height. This critical height is approximately 35% of the coil separation. So for a 4-meter separation, TX, RX, the critical height would be already at 1.5, 2 meters. Yeah. So I think this is a remarkable finding. The resolution of the ground sensor is superior to that of airborne sensors, whereas the depth of expiration for airborne sensors is superior to that of the ground sensor. Okay, last point, the effect of multiple electric sources. We did a numerical study to understand how many grounded dipoles we need to resolve all features in a given numerical model. So the numerical model consists of 2 quarter spaces with a dipping contact. The quarter space on the left side is more resistive than on the right side. 400, 500 ohms on the left side, 100 on the right side, with a conductive, very, very conductive sphere immersed in the quarter space on the left side with 1 ohmmeter. So if we have only one transmitter, what would be the optimum position of this source to resolve all features? Here, in general, we get some resolution. We see the difference in the electrical resistivity between the 2 quarter spaces, and we also get an indicator that there is something very conductive. This improves for this position, also for this position, but it becomes blurry for this position already. But it comes back and improves for positions farther away from this high conductive feature. So if we would use all 11, so the question is how many transmitters we need to resolve all these features. If we would use 11, clearly all features are more or less perfectly resolved. If we would use 7, also all features are resolved. If we use 3, still all features are resolved. So finally, we need at least 2 transmitters, or maybe 2 transmitters are sufficient to resolve all features. I think this is also a remarkable finding. Tensor electromagnetics. In airborne electromagnetics, usually the direction of the electrical resistivity cannot really be resolved. I think it's only possible with a grounded electric dipole, which generates a current pattern that allows to decide about the direction, the value of the electrical resistivity in all directions. So this I call tensor electromagnetics. And it requires at least 2 dipoles laid out in opposite directions, north-south and east-west, to generate electric current pattern in the subsurface that makes it possible to resolve for the 2 directions of the electrical resistivity. Here I give you an example of measurements we have done in in Canada last year. We flew such a very dense pattern with flight lines perpendicular to the first one, and the blue, the resistivity obtained from the responses flown on the blue lines show that the resistivity is considerably higher by at least one order compared to the resistivity estimated and derived from the measurements flown along the red lines. The resistivity derived from the responses on the red lines, flight lines, show values below, around 1 ohmmeter, which is remarkable. This is the magnetic, the total magnetic intensity and the tilt derivative. And this is how it looks like if we plot all cross sections together. The result of the interpretation of this of the responses of the semi-airborne measurements indicated massive mineral ores at different locations in this survey area. Another direction for the future. It's a Desnex group proved in a project in Namibia, I think 2 years ago, that it takes only that a very deep depth of exploration, deep means 1 kilometer, can be achieved by using an optically pumped magnetometer. In this case, they use a McArrow from Geometrics, It's a total field magnetometer, but using the responses measured from this McArrow, they were able also to interpret the responses and transform it into a conductivity model. In combination with a shift sensor from Metonics, they prove in two publications, the sources are shown here. Both articles were quite recently published in Geophysics. They proved that it's possible to resolve the electrical conductivity structure from near surface down to 1000 meter. This is shown here. The model results on the upper panel shows results obtained from the shift sensor. The lower panel shows results obtained from the geometrics, the McArrow, and the center panel shows the results of the joint inversion of two sensors together. And it's amazing to see that for the McArrow, deeper situated geological structures or high conductivity zones can be resolved, whereas structures which are close to the surface are much more emphasized by the shift sensor. So the combination of both sensors allow to resolve the entire space between surface and 1000 meter. So area electromagnetics. I think drone-borne electromagnetics, especially semi-airborne electromagnetics, using a grounded electric dipoles allows to fully resolve the 3D structure. I think this is unprecedented. I haven't seen this by airborne electromagnetic measurements in the past. It gives a full 3D picture of, it has the potential to give a full 3D picture of the electromagnetic, of the electrical conductivity structure in the subsurface. And by using more than one source on the ground, it will be able in the future to get a much better and picture of the subsurface with a much higher resolution using semi-airborne electromagnetics. So summary, last slide, loop-loop mapping, usually only 1D. Semi-airborne additional sources increase resolution of conductivity. Array EM only visible on drones and economic with drones. Field setup, tensor EM instead of vector EM. And I'm very sure in the coming years, we will see many different implementations of drone-borne EM systems. So that's it. Thank you very much.
Yeah, Sergio, please unmute yourself.
Yeah, hallo Johannes, sehr gute Vortrag. Hi everybody. You made my day, Johannes. I have been talking about, I didn't use that name, tensor electromagnetics, but I have been talking about anisotropy for a very long time, for many years. So I think you're giving us a solution. You know, flying in orthogonal lines, it is the solution. You know, and you showed it here. So I'm very happy, and thank you very much, Johannes.
Yeah, thank you, Sergio, and I'm happy to have you here.
Thanks.
Haven't seen for a long time.
Yeah, yeah. Hopefully more frequently in the near future, especially with the tensor EM.
Thank you. I see Dennis, you have your hand up. You should be able to unmute yourself.
Good morning, Johannes. Well, it's morning where I am, a very early morning. Are you aware of the, I'm sure you're aware of the GAP Geophysics Australia semi-airborne dipole galvanic and induction loop TEM system? It measures total B field like the geometrics one you showed with a high sample rate optical pump magnetometer geometrics rather than using the coil system. This instrument, the SAM instrument, was developed 15 years ago by Malcolm Kadich, initially as a ground and helicopter system, but lately in the last few years as a drone system. It's been used successfully in many mineral exploration projects in Australia and Canada for the past 10 years and actually detecting ore bodies at the depths you're talking about. So actually my question is just how does total B field measurement compare against a vector coil drone system?
Yeah, Dennis, good to know you are here. I'm sorry, you are absolutely right. I should have mentioned GAP Geophysics because they are well known for their system for a long time. And by the way, they use a transmitter which is at least 5 times stronger than the transmitters we are using. I think it's in the order of 250 kilowatts. So, but I don't know how they can handle it. But maybe in Australia it works. Yeah, the big difference between the 3-component sensor and the total field sensor is the total field sensor. You don't measure the components, which would be important to know. So in the papers I have mentioned written by Kotowski and Raphael Rochlitz, they explain. They give a very good explanation how it works. Yeah, how to extract the response from a sensor which is able to measure only which measures only the total magnetic intensity. So the problem is as you know, the geometrics McArrow as a total field magnetic sensor. The biggest part of the response is made by the Earth's magnetic field itself, and only a very, very small part. And the Earth's magnetic field has a certain direction, yeah. The electromagnetic field generated by the transmitter makes up only maybe 10,000th or 100,000th part of the field vector of the Earth's magnetic field, and might have also another direction. So it's a little bit tricky and maybe too lengthy to explain it here. But everything, how they do it, it can be read in the paper by Kotowski and by Raphael Rochlitz. Yeah.
Thank you, Johannes. All right. So Alan says, great talk, Johannes. Thank you. Are they feasible in the Andes, for example? What about using drones to lay out E-field receivers like the Mars rover has done?
Yeah, we are discussing this, and generally this is possible. I'm having a project in the Caribbean now, and the area is very rugged, so we are considering this to lay out the cable using our drone, a heavy lifter drone.
Thanks. Alex Castal has entered a question. Many of these drone solutions seem to require multiple flights and many grounded bipoles. Can you comment about the economics of flying such surveys compared to more conventional TEMs or other electric sources?
Yeah. In my presentation, I think I showed that I'm favoring at least two transmitters. But it requires to fly an area 2 times. At a time, only one transmitter is operating. So once one transmitter is finished, we operate the second one, but we have to fly the area again. This is very effective if drones are used. Walking is not an option, and maybe manned aircraft, air platforms are also not very efficient. So I think if you are required to fly an area several times, a drone is the only way, the only economic way.
All right, thank you, Johannes. We have another question. I'm a master's student at Aarhus University in Denmark studying geophysics. I have 2 questions that I would really appreciate your insights on. First question, do you see semi-airborne drone technology as the future for electromagnetics and resistivity methods? If so, how can it be optimized to minimize noise and improve depth penetration?
The electromagnetic noise generated by the drone, especially by the electronic speed controller and the electric motors, is very well understood. In the last 2 years, we had a company project where we completely characterized this type of noise, resulting in a method that allows us to eliminate this noise. So it can be measured and eliminated.
All right, thank you. His second question is, from a career perspective, what is your opinion on the role of coding and software development in geophysics? How important is it?
Very important.
All right, thank you. We have another question. Multiple drones can be flown in tight synchronization. Could or should they fly multiple antennas on separate drones?
Yeah, I'm very sure. Unfortunately, I didn't mention this, but I have no personal experience with it. And I haven't seen it yet, only for magnetometers, but not for EM systems. It can be I think there is a big potential using a swarm of drones, maybe 5 or 10, carrying EM sensors and fly an area simultaneously. The phase differences measured between the antennas attached to different drones, if they are measured at the same time, may contain some secret features we don't know yet. I would encourage you to think about this.
All right, thank you. So we have another question in the Q&A box. To get around flying the survey twice with 2 different TX setups, how about operating multiple TX at different frequencies and deconvolving the RX signal? Kim, would you like to ask your question directly? You can raise your hand.
Okay. Yeah, what I was asking was to get around the problem of having to fly the survey twice with 2 transmitters, why not operate 2 transmitters simultaneously at different frequencies and then deconvolve them afterwards? I know GAP have tried that with their SAM system. I'm not sure how well it worked, but it's certainly something that is doable from the physics.
You mean to run 2 transmitters simultaneously, but using different frequencies.
Correct. Yeah.
Yeah, this is, of course, this is possible. Yeah.
Right. Okay, excellent. Thank you so much. Electric conductivity is a tensor with 6 different values. Is that a
So,
question or a statement?
I thought it was a
Sure.
statement, but Sergio, if you'd like to change that into a question, please raise your hand. Or a statement, he
Oh,
says.
it's a statement. All right. All right. Any last questions for Johannes on his very interesting presentation?
I might take this opportunity to make a comment, if I may, regarding the idea of flying many drones at the same time and looking at any phase differences, I think you put them as, Johannes, between the reception at each different position at the same time. I feel that there's an analogy there in marine CSEM where the network of seafloor electromagnetic receivers are active all at the same time with fairly precise timing. And in that context, the phase differences, the phase lag, if you like, between receivers, given a certain transmitter position, does actually contain quite a lot of information. It has, I've heard it described as like the electromagnetic velocity through the subsurface, which of course is related to resistivity. And it serves sometimes practically as a wonderful edge detector for certain structures. So I would imagine the same might be true of a drone EM survey with multiple receivers.
Yeah, thank you very much. This is a very, very important comment on this. So time accuracy, we have our time accuracy in the order of 50 nanoseconds.
So you need very accurate timing.
Yes.
Okay.
All right. Any last questions? Dennis, I thought I saw your hand up there for a second. If there are no other questions, going once, twice. All right. Well, thank you, Johannes. Thank you, Anthony. Thank you, all the attendees, folks that had questions and comments. All right. And I guess we will have further webinars coming down the line. So if you are part of the Europe geophysical community and you would like to be involved more with the SEG Europe Regional Advisory Committee, please just let me know. Let Johannes know, let Anthony know, and then we'll hook you up. So thank you so much. Have a great day.
Thank you, Laurie.
Thank you very much, everybody. Have a great day.
Thank you.
Bye.
Bye-bye. Thank you.